Okay, so in the last two videos, this is part three of the derivation of the T character table. We got this far where we came up with, again, ones across the board, of course, a totally symmetric representation, ones across the board in terms of their characters for gamma 1. And then we figured out gamma 4 was 3, 0, 0, negative 1. How do we do these other two? And we knew from the sum of the squares of the dimensionality that there are ones here. Okay, so at this point, the easiest thing to do is to put variables in here. Okay, you could test different functions, but there are no easy functions because x, y, and z transform together. You start getting into the realm of complicated trigonometric derivations and visualizations if you try to test other functions here. You have to go to quadratics. So the easiest thing here is to use our other character table rules and puzzle these out. So I'm going to give these um, just variables right now because we don't know what they are, and we can use our character table rules to figure out what these must be. So let's use the principle of orthogonality, right? And so let's start off with gamma 2 here. We know that gamma 1 dotted with gamma 2, all the dot products have to be equal to 0. Remember, these dot products are adjusted for the amount of symmetry operations in each class. So in this case, I would write down gamma 1, which is ones across the board. I would write down our unknown, gamma 2, right, with our ABCs. And then also to write the number of symmetry operations in each class, which is 1, 4, 4, 3. That just came from the top here. I know that when I do this, we have ones over here on the left. Those all go away. So I end up with multiplying by everything by 1 does nothing. So I can just eliminate that. All that has to be equal to 0. That ends up giving me 1 plus 4a plus 4b plus c, or this is plus 3c equals 0. I'm going to multiply that out. Okay, so that's one equation that I have. And then I can also do the same thing with gamma 4. Okay. And so, oops, sorry, that was gamma 1 I rewrote. So let's put gamma 4 in there. Gamma 4 is not gamma 1 by gamma 4, gamma 4 by gamma 2. Trying to figure out what gamma 2 is. We know what gamma 4 is, so we put in gamma 4, 3, 0, 0, negative 1, dotted with, again, gamma 2, our unknown. I'm coming up with a system of equations here to help us solve what these unknowns are. That all has to equal to 0. If we multiply out those constants, that's going to be equal to 3, 0, 0, negative 3. I just multiplied this vector by that vector. And so that gets me an equation that looks like 3, but look at these zeros. So plus 0a, that goes away, plus 0b, that goes away, minus 3c equals 0. And so that means 3 equals 3c, and so c equals 1. And so we actually already figured out what c is, equal to 1. Now, there's something quite interesting here. We can think about gamma 3. And gamma 3 actually has to be the same. It also has to be 1 because the exact same equations apply. We could write the exact same equations with now 1 comma d comma e comma f, right? And we would go through all these things, exact same equations, and we'd figure out f has to be equal to 1 as well. So we figure out both of these. So now we just have these 4 values to figure out left. And so we're going to use another rule in the character table. This rule, if you remember, says that look at my character table rule video if you don't remember this, but we don't use this rule as much, but it's useful for these times when you're really trying to puzzle things out. And it's the sum of the squares of the character of each irreducible representation multiplied by the number of symmetry operations in each class is equal to the order of the point group, which in this case is 12, right? 1 plus 4 plus 4 plus 3. So mathematically what that looks like, and I think I can work up here now is for gamma 2, let's figure out if that if that rule, let's apply that rule. So it'd be 1 squared times 1. So 1 squared here and times 1 symmetry operation and identity, plus a squared times 4, so 4a squared. 4 came from here, and a squared, the character squared, plus 4b squared plus 3 times 1 squared must equal 12. 1 plus 4 plus 4 plus 3. Okay, so let's simplify that now. We end up with 4a squared, we can factor out a 4, plus b squared equals 12 minus 3 minus 1 equals 8. So we get a squared plus b squared equals 2, actually. We divide 8 by 4. Okay. So at this point, let's go back to our equation here that we derived. We're just puzzling through equations. And we saw that this equals 0, this whole thing equals 0. But now we know what the value of c is. So we can plug in c. So we get 1 plus 4a plus 4b plus 3 times 1 equals 0. And so this is then going to simplify to, we have a 3 here and a 1 there. We put those over on the other side. 4 times a plus b, right, factor out 4, equals negative 4. I move that to the other side. That tells us that a plus b is actually equal to negative 1. Okay, divide by 4 on both sides. Or in other words, b equals negative 1 minus a. So then we can go back up to here and substitute that in for b. A squared equals negative 1 minus a squared equals 2. Okay. All right. And so now we can factor out things. We have a quadratic type of formula. We factor out this term here. That's going to get us a 1. We got a plus 2a because we have negative a. The cross term is negative a times negative 1. That gets us a, and we do that twice. So that gets us plus 2a, and then plus a squared equals 2. We combine these 2a squared terms, move over the 2, and we get 2a squared plus 2a minus 1 equals 0. Now we use the quadratic formula, which we know is negative b plus or minus b squared, plus or minus the square root of b squared minus 4ac all over 2a. Right? This is our a coefficient is 2. This is our b coefficient is 2. This is our c coefficient is negative 1. So to do negative 2, that's our b coefficient, plus or minus the square root of b squared, which is 2 squared, minus 4 times a times c, all over 2 times 2, because 2a. Well, that equals negative 2 plus or minus, let's simplify this part, 4 squared, 2 squared is 4, so 4 minus, and this becomes 8, square root of negative 4 all over 4. Well, square root of negative 4 is equal to 4 times, square root of 4 times negative 1. Square root of negative 1 is I, and square root of 4 is 2. So you end up with negative 2 plus or minus 2i over 4, which we can simplify if we want to negative 1/2 plus or minus 1/2 I. So we got an imaginary solution here. So, I mentioned in part 2 of this video why this character table is more complicated, because we're getting imaginary solutions. Now, here's what it takes in order to derive this character table. Quite a lot of experience with character tables with imaginary numbers. And I have a video on this where I explain how when you have imaginary numbers in character tables, the rules change slightly. Okay? And so one way that the rules change is, please see that video, right? But one of the ways that the rules change is that this actual equation doesn't become true. So this is actually not the right answer. But we would not have known that because we didn't know a priori whether or not we had imaginary characters. Or complex is technically a complex number, right? Because that's a real and an imaginary part. So if you have a complex or an imaginary character, this rule is actually not true. And there's a modified version of this rule that's true because what it's telling us now is that these actually are bracketed together. These are two imaginary components of actually what we'd call just one gamma here. That's how these are typically written, at least in character tables. So these are like two components of one character. And when you sum them together, then they embody some more of the symmetry operations of the character. See my other videos where, I talk about this a lot whenever we have character table derivations with complex numbers. But anyway, we wouldn't have known a priori that this rule was false because it would have been true if we did all this math and we got a real number. But because we got a complex number, well, we know that this rule must be wrong. And the modified version of this rule, again, see my character table rules video, I call it special rule 5, is that this actually has to be equal to 0, not the order of the point group, okay? And so we'll get 1 squared now, we do this again, modify this, times 1 plus 4a squared plus 4b squared plus 1 times 1 squared equals actually 0. So same form of this equation, but instead of equaling the order of the point group, now we have to make it equal to 0. So what this math is going to come out to is quite similar form. We're going to factor out a 4, but now this is going to become a -4, right? Because we have 3 and 1, we subtract 4. And so now we get a squared plus b squared equals -1. Instead, all this part is the same, but we have not 2 here, but -1. So we're going to get a squared plus 1 plus 2a, I'm just copying this bottom line, right? Plus a squared equals -1. And now our quadratic formula, our polynomial just looks a little different. Now we have 2a squared plus 2a minus 2, plus 2, move that over, equals 0. We can factor out a 2 here. So we get a squared plus a plus 1 equals 0. And now we apply the quadratic formula once again. And when we do this, this time we get b is -1. -1 plus or minus b squared, so 1 squared minus 4ac, 4 times 1 times 1, all over 2a, all over 2. What does that get us? That gets us 1 minus 4, well, that's square root of -3. That's going to be 3i, right? Square root of -1, but that's going to be root 3i, right? Just to be clear, right? Root -3 equals root 3 times root -1 equals root 3 times root -1, and root 3 -1 by definition is I. So we're going to get -1 plus or minus root 3i over 2, which we can also write as -1/2 plus or minus root 3 over 2i. Now, anytime you see the values 1/2 and root 3 over 2, you should be thinking trig in your head. Those are common, unit circle stuff. And so this value is actually, so there's two solutions here, right? -1/2 plus root 3 over 2i, and -1/2 minus root 3 over 2i. And so what it's telling us here is that, hey, the value of, what are we solving here to remind us? We're solving for a. This could be the plus root or it could be the minus root. But if we did this same math, so that's cool that we got two solutions, because the same math would apply for this bottom component of the vector of the gamma 2, 1d(e)(1). So one of the roots we're going to ascribe to a, and the other root we're going to ascribe to d. Which one do we ascribe to which? It doesn't matter, right? That's arbitrary. But that's cool that we got two solutions naturally when we actually needed two solutions. Okay. All right. So, but we can simplify this. So we could plug that into the character table, but right now, but the way that people write this out is they use Euler's formula in the character table. And so Euler's formula says that e to the theta I equals cosine theta minus I times sine theta, one of these powerful expressions in math. And so this value ends up equaling, or these values are related to e to the 2 pi I over 3. Theta has to be 2 pi over 3. Because look at this. When cosine 2, when theta is 2 pi over 3, then you get plugging in 2 pi over 3 here. And if you solve for this, cosine 2 pi over 3 is, lo and behold, negative 1/2. There's our negative 1/2. And then you get sine of 2 pi over 3 is root 3 over 2. So e to the 2 pi I over 3 is just, e to the 2 pi I over 3 is just a compact way of writing negative 1/2 minus root 3 over 2I. So we're actually going to define a value called epsilon, you could call it whatever you want, and call that e to the 2 pi I over 3. This is how people write these character tables, just in a very compact form. And so now we can put that as our solution for A. That's what we solved. That's one of our roots. And we just said that our other root is where the imaginary component is negative. That's the definition of a complex conjugate. So epsilon complex conjugate, we use this star, is equal to, all you do is you make the root here, the imaginary part of your answer, the negative of it. So that would be, in this case, positive. And so we would get a positive value. So that can be our other root. That can be what we put for D. So to write this in a complex way, we just write epsilon star. All right, we're almost done. Now we just have to find B and E. And what we're going to do is just use this very simple formula here. A plus B has to equal to negative 1. Well, we know then that B equals negative 1 minus A. And we know what A is. It's epsilon. So we just have to do negative 1 minus epsilon. Well, what is epsilon? It's right there. Negative 1 minus negative 1/2 minus root 3 over 2I. Well, that is negative 1 minus a minus 1/2 gets you minus 1/2. And then you got a positive. The minus sign makes this a positive. What did it get you? It got you the complex conjugate. So B is actually equal to the complex conjugate of epsilon. Very similar thing is going to happen with E now. If you solved all these equations, right, and remember all these equations applied for 1 comma A comma B comma C, and also 1 comma D comma E comma F, you get the same thing, and you get an equation that says D plus E equals negative 1. Well, we know what that answer is already. We know epsilon plus epsilon complex conjugate equals negative 1. So here we have epsilon complex conjugate, so our unknown is going to be epsilon. And again, all this is with the definition of epsilon being equal to e to the 2 pi I over 3, or you can write that as negative 1/2 minus negative root 3 over 2I. And that is the derivation of all the characters in the T character table. Last thing we have to do is assign Mulliken symbols. These are pretty straightforward. We only have 3 of them to assign. If you have a Mulliken symbol with a dimensionality of 1, remember the dimensionality is the character underneath the identity class, you give it a value of A or B. You give it a value of A if you have a character irreducible representation that's symmetric with respect to the principal rotation axis. Principal rotation axis is C3. You're symmetric, you're a positive value, so you give it an A. If this was a negative one, you'd give it a B. If you have a character under the identity class that is 3, you give it a Mulliken symbol of T. And if you have a character that is E, okay, a character that has 2 under the dimensionality, you give it a value of E. You treat this together, you treat this as the sum. We broke this up into imaginary components, and it's a sum. And if we look at kind of the sum of E, that would give us a character of 2. We know epsilon plus epsilon complex conjugate is -1, and we know 1 and 1 is 2. And so, you know, some of these other character table rules will apply at that point when you look at the sum. For example, if we look at the dot product of the sum of E together with A, that should equal to 0. So we go 2 dotted with 1 dotted with 1 is 2, -1 dotted with 1, 4, that gives 4 plus -2, that gives us a -2, and then we'll have a -4 there. That's going to give us -6, plus 2 times 3 times 1 gets us 6, it gets us 0. If you dot it with T here, this sum, you're also going to get dot product is going to be equal to 0. So those character table rules apply, and the individual components, there are different rules there. Remember, and when you have these special characters, actually those so things change a little bit. So you can see my previous video on that, but here's how we're able to drive the whole T character table. Even though the math ends up pretty complicated, the mechanics behind it, I think, were fairly straightforward. It just did not require us to do any complicated derivations in terms of trig that are hard to visualize in 3-dimensional space, where I think that's really where it gets tricky. So anyway, I think this one is kind of cool.